This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to continue discussing the topic of energy, and specifically here we'll introduce the concept of gravitational potential energy, see how we can use that with conservation of energy, and then we'll also discuss power. First video on energy, we talked about why energy is a useful concept. And just to remind you, the reason is that energy is conserved. What that means is that energy is not created or destroyed, but simply it can be transformed from one type of energy to another or transferred from one object to another. The total amount of energy stays the same. In our last video, we used that with the concept of work to do some problems. Now we're going to learn how to do a different type of problem by introducing the concept of potential energy. So, first of all, when you hear the term potential energy means stored energy. In our first video, we talked about two types of potential energy: gravitational potential energy and chemical potential energy. Both of those are stored energies. In this video, we're going to be specifically talking about gravitational potential energy. So gravitational potential energy is the energy something has due to gravity. In other words, due to being a certain height off the ground. And the way we calculate potential energy is we just take the mass of the object, multiply it by g, the acceleration due to gravity, and multiply it by how high off the ground the object is. So if I've got an object some height h off the ground, then if that object has a mass m, I can simply calculate the potential energy there. I want to remind you of something we did in the last video. We calculated how much energy it took to lift up an object to a certain height by doing work on it. And one of the questions you might have had there was, well, if I lift an object up and I do work on it to do that, where did that energy go? Well, now you know the answer. It went into gravitational potential energy of the object. So this object has energy here because at some point work was done to raise that object up. Okay, so let's see how we can do problems with this new concept. Here's the first question. What's the potential energy of a ball that is held 2 meters above the floor if the mass of the ball is 1.5 kilograms? So we'll draw a picture. Here's our mass. Mass m is 1.5 kilograms. And we're told that it is 2 meters above the floor. So h is equal to 2 meters. To calculate the potential energy, we just use our formula, P equals mgh. And so we take the mass of the object, multiplied by g. Remember, g here on Earth is always 9.8 meters per second squared, times a height of 2 meters. And if you calculate that, you should get 29.4. Remember that our unit of energy is the joule. So that would be the potential energy of that object at that height. So why is this useful? Well, let's see. Let's look at the case of falling objects. When an object is falling, what's happening is one type of energy is being converted into another. Remember, we know that kinetic energy is the energy of motion. So if we start out and we have our object at a certain height, it's going to start out with all potential energy. But as that object falls, it's going to be losing potential energy and gaining kinetic energy. And we can write out a formula that basically specifies what we mean by conservation of energy in this type of problem. In other words, the energy stays constant. So at any time, if we add up the potential energy plus the kinetic energy, it's got to be equal to the potential energy plus the kinetic energy at any other time. Let me make this a little more concrete for you. Let's say that this object at the very top has a potential energy of 100 joules. If that object is at rest, its kinetic energy is 0. And let's call that our initial value. Remember that we use that sub-zero or naught to mean initial. So I'll just remind you, naught means initial. Okay, so let's say that we start out with a potential energy of 100 joules and a kinetic energy of 0. If I now let that object go, we know it's going to start falling down to the ground. So let's look at when it's halfway down. Well, since potential energy equals mgh, you'll notice that the potential energy depends directly on the height. So if the object is half as high, it would have half as much potential energy. So halfway down, the potential energy would be down to 50 joules. But where is that energy gone? It's gone into kinetic energy. So in other words, the kinetic energy there would be 50 joules because the potential plus the kinetic has to equal the potential plus the kinetic that we had at the beginning. Let's look at what happens the instant that object gets to the ground. And let me just mention something about that. I'll just write the instant the object gets to the ground. Because you might be thinking, well, when it hits the ground, its velocity is going to be 0. We're talking about just as it gets there, not once it hits. So just as it gets to the ground, you'll notice now h would be 0, so it no longer has any potential energy. So therefore, where must all the energy be? It's got to be all in kinetic energy. And that should make sense to you because you know that that object is going to be moving its absolute fastest right as it gets to the ground. So that's kind of a conceptual way to look at this. Let's go ahead and try out a problem. A 2.5 kilogram ball is dropped from a height of 6 meters. What is the initial potential energy of the ball? What is the initial kinetic energy? Okay, so that's pretty straightforward. The initial potential energy, and I'll put a naught there just to remind me that it's initial, just mgh. The initial height, I could actually put a naught there just to indicate initial height. So the mass is 2.5, g is always 9.8, and the height is 6. So if you calculate that, you should get 147 joules. That would be the initial potential energy. What's the initial kinetic energy? Well, again, we're dropping this object. So the initial height was 6 meters, but since we're just dropping it, the instant we drop it, it's not moving. So the initial velocity would be 0. And therefore, the initial kinetic energy, in general, we know kinetic energy is 1/2 mv squared. But if that initial velocity is 0, the initial kinetic energy definitely is 0. Okay, let's continue with the problem. When the ball is halfway down, what's the potential energy? What's the kinetic energy? And how fast is it moving at that point? Okay, so let me draw a picture. Again, here we have our initial position. That's when it was at a height of 6. We now want halfway down. So now y is equal to 3 meters. So our initial height was 6. Now we want to look at it when y is equal to 3. And I'll just remind you what we know so far. We know the initial potential energy was 147 joules. The initial kinetic energy was 0. So let's figure out what the potential energy is at this point. Well, PE is just equal to mgy. And you'll notice here that the only thing that's changed is that height. So I've got 2.5 for kilograms for the mass times 9.8. But now I'm only multiplying by 3. And when I calculate that, I get a value of 73.5 joules. So that's the potential energy when it's halfway down. Let's look at conservation of energy. We know the initial potential energy plus the initial kinetic energy has to be equal to the potential energy plus the kinetic energy at any other point. And so we're just comparing the 2 points. At the top, we know the potential energy is 147. The kinetic energy is 0. Then halfway down, we figured out the potential energy is now 73.5. And what we want to know is what the kinetic energy is. So you'll notice all I need to do is subtract 73.5 from both sides. And I get that the kinetic energy is equal to 73.5 joules. Once I have the kinetic energy, now I can find how fast it's moving. Remember, kinetic energy is 1/2 mv squared. So that's my starting point. But what we want to know is how fast. In other words, we're looking for v. So let me solve this algebraically. Again, I'm going to divide both sides by m. And I'm going to reverse the order here. So I'll write that as 1/2 v squared is equal to ke over m. Now I'm going to multiply both sides by 2. And that's going to give me v squared is equal to 2 ke over m. Or v is equal to the square root of 2ke over m. So let's plug in those the values. V is going to be equal to the square root of 2 times 73.5 divided by the mass, which is 2.5. And when you check that with your calculator, you should get, rounding off, that the velocity is 7.7 meters per second. So that's how fast the object would be going when it's halfway down. Continuing the problem, we now want to know what's the potential energy the instant it reaches the ground, what's the kinetic energy at that time, and how fast is the object moving. So again, we started out with the object with an initial potential energy of 147 joules and an initial kinetic energy of 0. So when it gets to the bottom, we know the potential energy is 0 because it's right at the bottom. But remember, it's the instant that it gets there, so it's still moving. So now I'm going to use my conservation of energy. PE naught plus KE naught equals PE plus KE. And let's plug in what we know. So again, what we're trying to find is what is that final kinetic energy. Well, you can probably see what it is already, but we'll just write it out. We've got 147 plus 0 is equal to 0 plus KE. So KE is 147 joules. That should make sense because in this problem, if we're going all the way from the top where the object wasn't moving to all the way at the bottom where it's basically right at the ground, all of the potential energy has now been converted to kinetic energy. And again, that's what we mean when we talk about conservation of energy. Let's figure out how fast it's going. We'll cheat a little bit here. We'll just say from the last slide, we had figured out that starting at ke equals 1/2 mv squared, we could use algebra to show that v is the square root of 2ke over m. By the way, this is a strategy, on an exam. Once you figured that out once, just keep a note of it if you need it in a different problem. So in this case, v is equal to the square root of 2 times 147 divided by the mass, which is 2.5. And if you work that out, you should get 10.8 meters per second. So that would be our final velocity, the velocity that object has just as it gets to the ground. So again, we're always talking about right as it gets there, not once it's hit the ground. Here's a related kind of problem, which is, what if we look at an object on its way up as opposed to an object on its way down? Here we have a 1 kilogram object, and it's being thrown up from the ground with an initial velocity of 6 meters per second. And the question is, how high up will it get? So what is its final height going to be? Well, again, let's think about what we know. We know that when it's right at the bottom, the potential energy, so this is going to be our initial potential energy, is 0, because our initial height is 0. It's starting from the ground. The initial kinetic energy we can figure out. Ke initial is just 1/2 mv initial squared. So that's 1/2 times 1 times 6 squared. And if you calculate that, you should get 18 joules. So that's our initial kinetic energy and our initial potential energy. Now let's think about what we know at the top. When it's at the very highest point, what's true about the velocity? Well, if you think about it, at the very top, that's where the velocity is going to be 0 for an instant, because that's where it would turn around and start coming back down. So we know the final kinetic energy is 0. Let's figure out what the final potential energy is. Well, here we're just going to use our conservation of energy. The initial potential plus the initial kinetic is equal to the final potential plus the final kinetic. And you can probably already see what the answer is going to be. In other words, the initial potential was 0. The initial kinetic was 18. The final potential energy is what we're looking for, and the final kinetic energy is 0. So the potential energy is just 18 joules at the top. And so now we can take that and figure out the height. We know that potential energy is mgh. And so if we divide both sides by mg, we learn that h is equal to the potential energy divided by mg. So we can do that math. We have 18 divided by 1 times 9.8. And if you calculate that, you should get a final height of 1.8 meters. So that's our answer. Let's look at another example of conservation of energy. This doesn't just work if we're throwing an object up or dropping an object and letting it come down. Let's say that we have a roller coaster. And so I'm just going to kind of draw some type of a roller coaster. And let's say that this is the ground level here. So our conservation of energy has to be true. By the way, if there were friction here, it's a little different, but we're only going to look at the case of no friction. Let's say that our little roller coaster here starts out and it has an initial potential energy of 1,000 joules. And it's initially at rest, so its initial kinetic energy is 0 joules. What would be true for the roller coaster when it's all the way down here at the bottom? Well, just like when we're dropping the ball, if it's all the way at the bottom, the potential energy would now be 0. And therefore, all of that initial potential energy would now be kinetic energy. So you notice we don't even really have to do math to do that. We can really just kind of see it by looking at the formula. Let's say that this is the halfway point. Well, we know that if it's halfway, it's lost half its potential energy. So there the potential energy would be 500 joules, and therefore the kinetic energy would be 500 joules as well, because the total has to add up to 1,000. And so notice that this describes what happens if you were riding this little toy roller coaster here, that the farther down you get, the faster you're going. But now as we start going back up this hill, we would slow down. We wouldn't come to rest because we don't get all the way up to the same height. By the way, without friction, if I just had a ball and I made a path like this and I let the ball go here, that ball would just roll back and forth forever, where it would simply get to that same height on the other side. So again, this would be converting potential to kinetic back to potential. And if it's somewhere in the middle, it's a mix of potential and kinetic energy. The last thing we want to talk about in this video is the concept of power. Power is the rate that we use energy. And so whenever you hear the term rate, it always means something over time. So an interest rate is how much interest you earn over time, for example. And so here, power is just equal to the energy divided by the time. Let's look at what the units of power are. Well, we know that energy has units of joules and time has units of seconds. So the unit of power would be a joule per second. But power is a really important quantity, so we give it its own unit called the watt. So 1 watt is equal to a joule per second. So I want you to think for a minute, where have you seen that term watts before in your house? Well, you might have come up with a number of different answers. Maybe on your hair dryer it says 1600 watts. Maybe probably the most common answer is usually a light bulb, because if you look at a light bulb, it will tell you something like it's a 100 watt light bulb. Really, any electrical device will have a power rating on it. And what that's telling you is simply how many joules of energy that uses per second. So if you have a 100 watt light bulb plugged in, it's using 100 joules of energy for every second that goes by. Let's try out a few problems using the concept of power. So let's start out with a light bulb problem. It says a 60 watt light bulb is left on for 5 hours. How much energy does the bulb consume in joules? So one of the things that we've talked about previously is this idea of you've got to have that table in your head of quantity, symbol, and unit. And here's a good example of why that's important. Notice that we know that power has a unit of P, has a symbol of P and a unit of watts. Well, notice here that I don't tell you this is the power. You have to be able to look at that and say, oh, it's units of watts. That means power. We're told that the bulb was left on for 5 hours, so that's T. But we know that time has to be in seconds when we're using that formula. And notice that what we're being asked for is the energy in joules. So we're trying to find the energy. We know the power and we know the time, but we don't know the time in the correct units. So the first thing I might do is just take my time. I've got 5 hours, and let's go ahead and do our unit conversion. We know there's 60 minutes in 1 hour, and we know there are 60 seconds in 1 minute. So hours cancels with hours, minutes with minutes, and if I just multiply that out, I'll get the time in seconds. and you'll notice that we get 18,000 seconds. Okay, so now I've got the time in the correct unit. Let's write down our formula. Power equals energy over time. Now, what we want is energy, so let's go ahead and solve for energy. Notice I'm going to multiply both sides by t, so those t's will cancel out, and I get that energy is equal to power times time, or time times power, it doesn't matter, but I usually write it that way. So now I can just plug in my values. I've got a 60-watt light bulb. I'm multiplying by 18,000 seconds, and that's a lot of energy. That's 1,080,000 joules. Probably be good to put that in scientific notation. So let's count 1, 2, 3, 4, 5, 6. So that'd be 1.08 times 10 to the 6th joules. Again, in our last video, I talked about the fact that a joule is a small amount of energy. So you'll notice if the only thing you did in your house was had one light bulb on for 5 hours, you're already using an awful lot of joules. Let's try another problem. This one says a microwave oven uses 72,000 joules of energy in 1 minute. What's the power rating of the microwave? So we're looking for P. Notice that what we've been given is the energy, so we know E. We've been given the time, but it's not in the right units. So let's convert that time first. This is pretty easy because we know that in 1 minute there are 60 seconds. And so 1 minute is simply 60 seconds. Okay, so we're trying to find the power. Our formula is P is equal to E divided by T. So we're already solved for what we want. We just take our 72,000 joules and divide by 60 seconds. And if you do that, you'll get 1,200. And again, our unit for power is watts. Now, by the way, if you look on your home microwave on the back, you can see what the rating of your microwave is. 1,200 watts is a pretty typical rating for a microwave oven. So again, that means that that microwave oven is using 1,200 joules of energy for every second that you have it on. One last problem. Why don't you pause the video and see if you can do this one on your own, then restart the video and see if you got it right. Okay, so a laptop charger uses 65 watts of power, so clearly we've been given P. Notice, by the way, I could have said that question without using the word power. I could have said a laptop charger is rated at 65 watts. And then again, you'd have to know, oh yeah, watts is power. If it charges a laptop for 3 hours, so that's our time, but not in the right units, how much energy does it consume? So we're looking for E. So let's go ahead and do what we usually do, which is let's first fix our time. We've got 3 hours. We know there's 60 minutes in 1 hour. We know there are 60 seconds in 1 minute. And so if you multiply that out, you should get 10,800 seconds. Once we've got that, we'll start with our equation. Power equals energy divided by time. But again, we've got to solve this for E. So I'm going to multiply both sides by T. And I get that energy is power times time. And now I just need to plug in the values. So we've got 65 watts times 10,800 seconds. And if you calculate that, you should get 702,000 or 702,000 joules. And of course, probably be good to leave our final answer in scientific notation. So that's 1, 2, 3, 4, 5. And so our final answer would be 7.02 times 10 to the 5th joules. Okay, and that's our last problem for today.